Hey guys, Mr. Antonucci here, and in this video we're going to cover section 1.1 graphs and models. And the first thing we're going to do is review sketching the graph of an equation. Now there's several ways to graph a function. The first is just by plotting points. So for example, if we wanted to graph the equation y equals x squared minus 2, we could make a table of data to organize our work. So we could have a table of x values and y values, and if we pick some negatives, 0, and some positives, we could get a good idea of what it would look like. So if you plug -2 in, squared is 4, minus 2 gives you 2. If you plug -1 in, you would get -1, 0 gives you -2, and then the rest would be -1, 2, and 7. So if we went ahead and plotted these points on a graph, so on the graph if we start plotting these points, -1, -2 goes with 2, -1 goes to -1, 0 goes to -2, 1, -1, and then we just continue on, 3, and then 7. And if you connect them with a smooth curve, you'll see you get a parabola. Now, the issue with this kind of approach is that you may miss important features of the graph by just plotting points. Also, it can be very tedious. For example, if we wanted to graph this equation, which is a little bit more complicated, plugging in the points would start to get very tedious. But also, if we just picked 5 points like this and we plotted them, it would look deceptive because it would look like the points go into a straight line. However, if we actually graph the function using technology, we'll see that is not what the graph looks like. It actually has some curvature to it as well. So another approach is to use technology such as Desmos or a graphing calculator, and I'll be modeling things with Desmos. Again, there is a downside to these, is that the viewing window that you have may misrepresent the graph and some important characteristics may be missed. So we want to graph these two equations using Desmos. Let me pull that up. Okay, so I have the first graph here. It's the cubic, and if you graph it in the standard 10 by 10 viewing window, you just see this part of the curve here. Now if we start to zoom out, you can see more features of the graph, but the standard beginning viewing window, you don't see it all there, so you could miss those features. If I look at this graph, the second one, it doesn't show all of the graph, so we would actually have to move around to see the minimum on the graph. Another thing is that at x equals 3, you would be dividing by 0, so that's an excluded value. You can't see that on the graph, but when x is 3, if I click on the graph and I drag the point till x is 3, you can see that it actually should be undefined there, but the graph doesn't just show that. So in these cases, it can be difficult to know what to look for. So a better approach that's even more helpful is an analytical approach, and this is why knowing about symmetry, intercepts, roots, maxes, and mins, as well as domain, range, domain restrictions, discontinuities, and other analytical tools are going to be very helpful in analysis of graphs. And we're going to look into a lot of these tools during this course. The next thing we want to look at is finding the intercepts of a graph. So a couple things to keep in mind here. Intercepts are the points where the graph crosses a coordinate axis. If it's an x-intercept, it's always going to have the form of the number where it crosses the x-axis, comma, 0. And y-intercepts are kind of the reverse of that. It's always going to be 0, comma, the number wherever it crosses the y-axis. Now graphs can have none, 1, 2, several, or infinitely many intercepts. So we can use what we know about intercept coordinates to help us determine the intercepts of a graph. So for example, if I want to find the x and y intercepts of the function x cubed minus 4x, the first thing to do to find the x-intercepts is I can set the equation equal to 0 and solve for x. First thing we're going to do is factor out an x. So you'd have x squared minus 4 equals 0, and then that's a difference of squares, so that's going to be x minus 2 times x plus 2. And then we set each of those factors equal to 0, so we would get x equals -2, 0, and 2. So that would result in the points -2, 0, 0, 0, and 2, 0. Notice all of them have a y coordinate of 0. To find the y-intercepts, all we do is let x equal 0. So if we plug 0 in for x for this equation, so 0 cubed minus 4 times 0, it's pretty simple, straightforward. You get y equals 0, and that's actually the coordinate 0, 0 that we already got when we found the x-intercept. And basically the graph just is going to pass through the origin in that situation. So the next thing we want to look at is testing a graph for symmetry with respect to an axis and the origin. The reason symmetry is important is because it can greatly reduce your work in graphing a function if you know some of the concepts of symmetry. There's basically 3 types of symmetry we're going to look at. Y-axis symmetry, where the graph is basically a reflection of itself over the y-axis. And this basically means if xy is a point on the graph, so is -x, y, because the opposite x value will produce the same y value. X-axis symmetry is similar, it's just a reflection over the x-axis. So if the point xy is on the graph, the point x-y is going to be on the graph. And then the third one is origin symmetry, and this is a situation where if the point xy is on the graph, then the opposite of x, opposite of y is going to be a point. And basically, if you think of putting your finger on the origin and spinning the graph 180 degrees, it should land right on itself. So the first thing we're going to do for an example here is test the symmetry of the graph of y equals 2x cubed minus x. Now the first thing we can do is test it for the y-axis, and in this case we're going to have the original equation, but we're going to replace x with -x, so this would be 2 times -x cubed minus -x, and that's going to simplify to -2x cubed plus x. So when we simplify this, it is not the equivalent equation, so it is not symmetric with respect to the y-axis. Now we're going to also check it with respect to the origin. And in this case, we're going to take the original equation and replace y with -y and x with -x. So -y equals 2 times -x cubed minus -x. And the -y doesn't really have anything to simplify, and this side's going to be -2x cubed, because a negative cubed is a negative, and then plus here. Now if we solve this for y, you would just divide by the negative, which really you could think of that as a -1. So you'd have y equals 2x cubed minus x, which you got the equivalent equation. So when we replaced x with -x and y with -y, we got the equivalent equation. So that means this graph is symmetric with respect to the origin. So we'll show that to you on Desmos. Okay, so we can see that the graph here is symmetric with respect to the origin. If we were able to rotate this 180 degrees, it would land right on itself. General rule of thumb with polynomials is that if all the exponents are even, then the graph has y-axis symmetry. If all the exponents are odd, then the graph has origin symmetry. And I would add that if there is a mix of even and odd exponents, then it's not going to be either one. Another example is a situation where you may not have y as a function of x. If we want to use intercepts and symmetry to sketch the graph of x minus y squared equals 1, this is how we would go about that. The first thing we would do is replace y with negative y, because we might think that this graph is symmetric with respect to the x-axis. So x minus negative y squared equals 1. When you square a negative, you get you get itself. So negative y squared is just going to be minus y squared. So that equals 1. Don't need that parenthesis there. So we got the original equation, and that means the graph is symmetric with respect to the x-axis. Also, if we want to check out the intercepts, when I replace x with 0, so you get minus y squared equals 1, you have y squared equals negative 1. That doesn't have any solution, so there are no y-intercepts. So when I replace y with 0, I get x minus 0 squared equals 1. So x equals 1 is the x-intercept. So I know that x equals 1 is the x-intercept. If I grabbed a couple more points and use the fact that there's symmetry, so for example, when x is 2, the y value is going to be 1 or negative 1, so that would give me a point there and a point there. And when x is 5, the y value is going to be 2 or negative 2, so that gives me a point there and a point there. And it's basically going to look like a sideways parabola starting at x equals 2. And we'll check that with Desmos. Okay, here's the graph right here. If we zoom in a little bit, you can see that it's a sideways parabola, symmetric with respect to the x-axis. It starts at x equals 1 and opens to the right, and you can see the symmetry there. So the last thing we want to look at is finding the points of intersection of two graphs. This is basically like solving a system of equations, and graphically this is where the graphs meet or cross. So they're going to share that point, so they share a solution. So if we want to find the points of intersection of the graphs of x squared minus y equals 3 and x minus y equals 1, what we would do is solve each equation for y first, set them equal, solve for x, and then get the corresponding y values. And we can also confirm this using Desmos. So the first equation is going to end up being y equals x squared minus 3. You could bring the y over and then subtract 3, and then I just rewrote it. And then the other equation is going to be y equals x minus 1. Did the same thing there. And since these are both equal to y, we can set them equal to one another. So x squared minus 3 equals x minus 1. Since we have an x squared, we would use, this is going to be a quadratic, so we could set it equal to 0 and see if factoring is going to help. So x squared minus x minus 2 equals 0. And in fact, factoring does work because we want factors of negative 2 that add to negative 1. So x minus 2 and x plus 1. And then by the zero product property, each factor can be set equal to 0 and solved. So we will get x equals 2 and x equals negative 1, and then to get the corresponding y values, we just plug them back into the original equations. I'm going to use the linear equation because it's easier to substitute into. So when x is 2, y equals 2 minus 1, so y is going to equal 1, so it would correspond to the point 2 comma 1. Also, when x is negative 1, do the same thing. You would get negative 2 for y, so negative 1 comma negative 2. And you could also verify that both of those points substituted into the x squared minus 3 are going to work as well. So we'll check this with Desmos. We have our first equation here. If I plot it, it's a parabola opening upward. The other equation, boom, right there. Now if I just click on the intersection points, you can use this function right there to copy it into the table over here. And then if I go right here, and you get the 2 points, -1, -2, and 2, 1, just to verify that we have both of those. All right, that's it. Hope that was helpful to you guys, and reach out if you have any questions, and take care.